So for the last couple of lectures, I have been exploring the question whether or not science describes reality. There's a separate set of questions I want to talk about for this lecture that are around the question of whether or not science should be trying to explain why things happen, not just what happens or what is the case, which is sort of the descriptive aspect of science, but the why questions, the explanatory aspect of science. Is it the business of science to explain things in the world? Now, the common sense answer to this question, of course, is, well, yes, duh, of course. What else is science going to do? Of course, science provides explanations. It does it all the time. You can probably think of a few potential scientific explanations off the top of your head. So that's the common sense answer. But if you've been paying attention this far, you're probably savvy enough to recognize that you can't really trust common sense when it comes to these things. These sorts of issues are often more complicated than they seem at first glance. Now, I touched on the question of scientific explanation in a previous lecture when talking about Thomas Kuhn. I noted that there was a discrepancy between the explanatory accounts given by René Descartes and the account given by Isaac Newton when it came to gravity. Descartes' theory of gravity had one thing going for it that Newton's did not. Descartes' theory of gravity actually provided an explanatory account of why objects fell. It actually wasn't too dissimilar in some ways from the ultimate account given by Albert Einstein. He sort of posited something kind of like a space-time continuum, and he sort of envisioned planets moving around the sun in much the same way that water will go down a spigot or a hole. It had other deficits, other flaws, of course. Newton's theory had a lot more accuracy than Descartes had, but it really had no explanatory value. Newton himself basically said, look, the job of science is not to explain things, it's just to describe them. Newton's gravitation equations give a very, very accurate account of why things fall, but no, it doesn't really tell a story about why they fall. And long story short, abbreviating the history tremendously, Newton ultimately won that debate. And for quite some time, the idea that science should explain phenomena was sort of thrown by the wayside. For some centuries, it was the thought that science was not really in the business of explanation. All scientists cared about, according to this sort of Newtonian picture, is giving a mathematical description of phenomena. It's not giving an account of why things behave the way they do. Now, future developments in science sort of started to turn this on its head, most notably perhaps Charles Darwin's theory of evolution and then Albert Einstein's general theory of relativity. Both of these seem, at least on their face, to provide explanatory accounts in addition to descriptive accounts of the phenomena in question. And so these sorts of developments then sort of shifted us back to this question about whether or not science should be explaining things. So before we sort of delve into the question of whether science should be explaining things, perhaps we should say something about what an explanation is in general, not just in science, but in any context. What does it mean for X to explain Y? And suffice to say, this is actually a lot harder question than it might seem like at first glance. There's actually a variety of different accounts of what an explanation is, and there is no sort of single winner here that satisfies everybody. So one idea about what an explanation is says that an explanation is any story that satisfies our desire to understand. Any time you sort of are looking for an answer, you're looking to make sense of something, anything that anyone tells you that sort of makes you go, okay, now I get it, anything that scratches that itch, as it were, is an explanation. Now, there's no doubt something to this. There's something about explanation that kind of obviously ties into the notion of understanding. If science is merely descriptive, it perhaps gives us knowledge, but it doesn't give us understanding. Understanding requires having an explanation of things, and that seems to run deeper than just knowledge in that sort of superficial sense of the word knowledge. Now, there's sort of potential counterexamples here. Aristotle's theory of gravity, for example, posits that the reason why stones fall down is because stones are returning to where they belong. Stones come from the earth, they belong to the earth, therefore they fall down. Fire, by contrast, rises because fire belongs in the heavens with the sun, with a big ball of fire up there. So stones fall because they belong on the earth, fire rises because it belongs in the heavens. That seems to fit this sort of notion of an explanation satisfies our desire to understand. Many people accepted Aristotle's theory of gravity for quite some time. But a lot of people want to say that, no, that's not really an explanation. A literary example might work here too. The French playwright Molière wrote a play called The Hypochondriac, and in this play, a character who is a doctor, a doctor to be, a medical student, is taking his medical boards, and he's very, very nervous. And the medical board asks him, "Why does opium put people to sleep?" And the character is very excited because he actually knows the answer to this, and he stands up in front of the medical board and says, "Because it has a dormitive virtue." And everyone applauds, and to much hilarity in the audience. Again, this is Molière's comic playwright, and Molière, of course, is mocking doctors here. He's mocking the idea that they ever really explain anything. This notion is that what appears to be explanation is really just a restatement of the problem. It's really just a pseudo explanation. Another good example here comes from Calvin and Hobbes. Calvin asks his father, "Why does the sun set?" And his father says, "It's because hot air rises. The sun's hot in the middle of the day, so it rises high in the sky. Then in the evening it cools down and sets." Calvin asks, "Why does it go from east to west?" "Solar wind." Now again, this is obviously sort of a comic exaggeration, but you get the idea, right? There's actually several of these comics where Calvin's dad gives pseudo-scientific explanations to his son. It sort of shows that, again, you can imagine Calvin being satisfied by his father's answers, in which case it seems like, these pretty clear pseudo-explanations aren't legitimate explanations. Therefore, this sort of, this idea of this satisfying our desire to understand account isn't going to be enough. So the sorts of stories that you get when you talk about Aristotle's theory of gravity, or any sort of folk theory about scientific explanation, or sort of religious mysticism or something like that account of things, these seem to satisfy people for some time. Aristotle's theory of gravity dominated for over 1,000 years. Now, one thing we might say is that, well, Aristotle was an explanation for that time when he was accepted, but he's no longer, his theory is no longer an explanation. I mean, that's not preposterous on its face, perhaps, but I think it's probably a more common belief is to say that they actually weren't explanations, they were pseudo-explanations the whole time, and people just mistook them for explanations. Now, again, that's not to insult people in the past. Pseudo-explanations can often be very hard to distinguish from real explanations, but that's sort of the point. It's really hard to know exactly what an explanation is. So let's try to unpack this a little bit by going back actually to the very sort of beginning of this lecture series, back to the logical positivists and their account of explanation, courtesy of the logical positivist Carl Hemple. As a general rule, the positivists were very, very skeptical of theories of explanation. And the reason why is because explanations seemed to be, again, like an invitation to metaphysics. And they very much did not like metaphysics. They wanted to stay as far away from metaphysics as possible. Explanation seemed to involve somehow going beyond the evidence. And they never wanted to go beyond the evidence. That was the whole sort of idea behind the logical positivists. They were strong empiricists. Everything was about evidence for them. They don't want to go beyond the evidence. But that sort of general caution having been said, the logical positivist Carl Hemple did try to provide a fairly minimalistic account of explanation, which is called the covering law model, or the covering law theory. Also, the deductive nomological model is the technical name for it, but I'm just going to call it the covering law model because it's easier. Now, the covering law notion is basically universally rejected by pretty much everyone for the same sorts of reasons that pretty much everything logical positivist is rejected these days. It was a major contender for a long time. It had many, many strengths, but ultimately it fell prey to a series of fairly decisive losses. I want to talk about it and give an explanation of it, but again, I want to sort of set it up first and then explain why ultimately it failed. So what is the covering law theory? What does it say? Well, in short, what it says is you can explain something when you show how you can derive that thing from a logical argument, from a deductive logical argument. That is to say that according to the covering law, an explanation is just a prediction in reverse. If you know the outcome, you can sort of reverse engineer the law, but that's going to sort of an inductive measure. It doesn't work, which has problems for David Hume and so forth that we saw before. But if you know the law, then you can predict the outcome. The sort of standard example here would be something like Newtonian mechanics, right? If you know Newton's law of gravity, then you can predict the rate at which two bodies will accelerate towards each other. That, according to Newton, wasn't an explanation, but according to Hempel, actually it is. If you know the law, you can predict the phenomena, and if you know the phenomena, you explain the phenomena by appealing to that law. So explanation is just prediction in reverse, according to Hempel. I want to unpack that's sort of the gist of it, but I want to unpack it a little bit more detail here, using some technical terminology. Hempel calls the thing to be explained the explanandum, and that is something you have to place at the conclusion of the argument, whereas the premises, the so-called explanans, do the explaining. So you organize the premises in the right way. These are the things that are supposed to explain the phenomena, and then the phenomena being explained, the explanandum, is the conclusion. Now, another important qualification here, again, as the covering law, the name law there implies at least one of the premises has to be a law of nature, and that law of nature actually has to contribute to the argument. It can't just be an appendage that you're throwing in there for no good reason. The law has to sort of entail in some ways the phenomena. Not every premise has to be a law. You can also have, of course, sort of background conditions, other details which contribute in some way to the explanation. But the law is the crucial step. You have to have at least one law in your argument in order to actually have an explanation. So you explain something according to this view when you show that it's to be expected, given what you know. Given that you know Newton's law of gravity, for example, then you would expect two bodies of a particular mass and distance from each other to accelerate at a given rate. That sort of follows deductively from the law. If you had all the premises in advance, you would have predicted it was going to happen. Oftentimes, of course, explanation works the other way. You have the phenomena, you don't have the law. You're trying to find the law because you're trying to find the explanation. When you find the law that explains the phenomena, then you have explained the phenomena. Let me rephrase that. When you find the law that accounts for the phenomena, you have explained the phenomena. That's all that there is to it. There's nothing more to explanation than simply understanding the laws that govern the behavior of the thing that you're trying to explain. Now, obviously, there is something to this. It is the case that I think it's fair to say that explanation works this way some of the time. But for reasons that we will hopefully become clear in the next few slides, it can't possibly be a satisfactory account of explanation in general. It cannot account for all cases of explanation. Or rather, if you want to insist that it does account for all cases of explanation, you're going to have to both include some things which don't on the face of it seem like explanation, and exclude some things which do on the face of it seem like explanation. So let's start with the physics bias objection. Again, I've said before in the past that many times the logical positivists have a clear physics bias. They clearly were enamored with the physics of people like Albert Einstein, and I think when they were thinking about the philosophy of science, they were sort of taking a physics-first approach. Now, there's nothing intrinsically wrong with that, of course, just so long as you recognize you're doing it and recognize that it might come with certain limitations. But I don't think that Hempel or the positivists really quite realized the limitations that they imposed on themselves by taking this physics-first approach. So the central point here is that this account obviously relies essentially on the notion of laws of science. Physics is very much a law-driven kind of discipline, but not all sciences really seem to rely on laws in the same way that physics do. Take biology, for example. There are certainly laws in biology, but not everything in biology appeals to law-like functions. So, you can presumably sort of explain human evolution by appealing to certain sort of our genetic ancestors, other primates, and then this kind of selective pressures that they were put under and so forth. You can tell a fairly detailed covering law account that would seem to explain this the evolution of human beings, but there's no law of biology, Darwinian evolution or otherwise, that says if you give this species and apply these pressures, then humans will evolve. There's just way too much noise, too much chaos in the system to ever sort of nail down a law like that. There's just too much randomness to account for in the world. You can't take a law-like approach to biology in this, Frank. I mean, even perhaps in some sort of abstract, principled way, if you knew all the laws of biology, all control for all the relevant factors, you might get something like that. But biology in the real world never actually works like that. It's taking you would be doing considerable violence to the actual practice of biology to say, well, in principle, you could do it this way and derive the law. Even if it's true that you can do that in principle, in practice, biology is so far removed from that kind of approach that that's simply not the way biology, as it actually works in the real world, works. Another example is history seems to offer explanations of historical events. You can, for example, explain the American Civil War by saying things like, well, there was a schism between the abolitionists and the anti-abolitionists over slavery, and there's various economic factors about, industrialized labor versus manual labor and so forth. You could give an awful lot of these conditions, but there doesn't appear to be any laws of history, at least not in the way that sort of give these kind of, if you have a country with slavery and a schism over slavery with these economic conditions, you will see a civil war followed by necessity. Again, for the same reason as biology, there's just too much noise in history. There's too many X factors that you can't control for, that if you tried to actually do history this way, you wouldn't get very far. The actual practice of history seems to provide actual explanations. Historians, I think, certainly would say they explain things all the time, but they do not explain things in the way that Hemple's covering law model suggests they should. It's also worth noting here, of course, one historian who did want laws of history here, of course, was Karl Marx. And, well, we saw how well his model worked out. Didn't work out quite so well, in no small part for this exact same reason. There's too much noise to say that history works in a law-like fashion. You could tell similar stories for disciplines like psychology, economics, geology, meteorology. Now again, to be clear, I'm not saying that there are no laws in these fields. There perhaps are, but the fields as a whole cannot be reduced to sets of laws. That's simply not the way it works, because in all of these fields, chance and chaos just sort of play too large a role. So, again, one thing which could be done, and for the record, this actually is what Hemple did. Hemple actually said that, no, these fields actually don't explain. These fields may describe certain things, but they don't actually explain anything. So Hemple bit the bullet on this one, which is a pretty bold move, but I suppose to his credit, there's nothing that says that you can't do that. It may be an uncomfortable position, but it isn't a logically impossible position or anything like that. I think the real death of Hemple's covering law model, though, came with the asymmetry problem, the asymmetry objection. I think this was the fatal objection to the covering law model. This was the one that really made even the logical positives stand up and take notice. So consider the question, why is this flagpole's shadow X meters long? So here's my graphic here. You have a flagpole, it has a shadow, and you're trying to explain the length of the shadow. Now, the length of this shadow can actually be explained in some fairly straightforward terms. You can deduce the length of the shadow from the following elements. If you know the height of the flagpole, the relative position of the sun, the laws of optics, and some fairly basic trigonometry, you can run a calculation and you can deduce the length of the shadow from those basic facts. Now, so far, this seems like a perfectly legitimate application of the covering law model. How do you explain the length of the shadow? Well, in terms of the height of the flagpole, position of the sun, laws of optics, and basic trigonometry. There's your deductive nomenological account of the length of the shadow. But notice the following. You can actually swap the explanon and the explanandum here. That is to say, you can actually explain the height of the flagpole in terms of the length of the shadow. You can rearrange the elements in the argument, and the logic is still perfectly valid. It works just as well. So if all that you need in order to make an explanation is to provide a logical argument using a law that entails the phenomenon in question, you can do that to explain the length of the shadow using the height of the flagpole, or you can explain the height of the flagpole using the length of the shadow. That just frankly kind of seems absurd to most people. Again, when first he encountered this objection, Hemple tried to bite the bullet on this one too, but it was quite frankly just, I think, ultimately too much, and this was sort of started to spell the beginning of the end of the deductive nomenological account, the covering law model account. So again, it was a courageous move on Hemple's part to try to bite the bullet on this problem. But when you really start sort of recognizing the scope of the problem, it becomes just unavoidable. So consider this example, which again I'm stealing from the philosopher of science Jeffrey Kasser here. Consider the relationship between symptoms and diseases in medicine. If you have Koplik spots, you can actually predict the onset of measles. You know that the person has measles. Koplik spots are a symptom of measles. But while measles can pretty clearly explain the Koplik spots don't explain the measles. The measles is explained by other virological terms. You don't explain a disease in terms of its symptoms. You can explain the symptoms in terms of its disease. It's a one-way street here. Symptoms are the results of diseases. Diseases are not the results of symptoms. But there's nothing in the covering law model that can account for this, sort of this one-way street. In other words, the asymmetry problem results from a fairly obvious fact. The height of the flagpole, which in this case is the same as the disease, causes the length of the shadow, which is the symptom, but not vice versa. So what we need, it seems, in our account of explanation is some way to roll the notion of cause into this story. Now, this creates a host of problems because causation is mysterious too, but this is a pretty good place at least to sort of start shifting. Once the covering law model fails, we have to start shifting to some sort of causation account.